part, what we will be discussing is how to generate the sequence of permutations or permutation generation technique, combination generation techniques, rearrangement generation techniques. I think that they have, what is permutation? This should be known to you. That permutation is the arrangement of odd elements out of n, right? So if you remember that if I have n elements, the elements are numbered 1 to n, and if you have to arrange these n elements, there are npn possible ways or distinct ways you can arrange them. Now, more generic one, that given n elements 1, 2, 3 up to n, I want to make the arrangement of R elements, right? So there are possible number of distinct permutation will be NPR, right? And this NPR is basically n factorial by n minus R factorial. So for example, suppose I have n equals to 4 and R equals to 2, then possible arrangements will be, say n equals to 4, the elements are say 1, 2, 3, 4, then possible arrangements will be 1, 2, 1, 3, 1, 4, then 2, 1, 2, 3, 2, 4, 3, 1, 3, 2, 3, 4, 4, 1, 4, 2, 4, 3. So these are the possible arrangements you have, right? So what is the basic definition or definition of permutation? Is nothing but this arrangement of R elements out of n. That gives you a permutation. And there is a term we'll be using, identity permutation. This identity permutation of n elements is nothing but 1, 2, 3 up to n. This is identity permutation. Now the two permutations are distinct. When can we tell that the two permutations are distinct? One, that the existence of one element is different from one permutation to another permutation. That means that suppose I have one permutation x1, x2, xr, and another permutation is y1, y2, yr. These two are distinct. One possibility is that all of them may be same except one of them is different. Right? The occurrence of all of them are same. Right? This is maybe 1, 2, 3, 4, 5, 6 up to R. Here it is 1, 2, 3, 4, 5, 6, 7, 8 up to R minus 1, and this is R plus 1. Then you can tell they are distinct. Or the arrangement of the same elements is different. That means all these elements occurred here, but occurrence position is different. Right? For this example, that 1, 2 is a permutation, 2, 1 is also another permutation, but the occurrence or existence of all these elements are here, same. Only the ordering is different. Right? If the ordering is different, then it is a permutation, or the elements are different. 1, 2 and 1, 3. These two elements are different. Then also it is a permutation. Now there is one word we will be using that is known as lexicographic permutation. So we take lexicographic suppose alpha is a permutation of R elements and beta is another permutation of R elements. Then alpha, we tell alpha precedes lexicographically beta if there exists a J such that xi is equals to yi, I is less than j, and xj is less than yj. So we tell alpha precedes lexicographically beta if there exists a j such that there exists a j here, xj, yj, such that all of them are safe, this is safe, but this one is less than this one. Okay? So, in permutation X, we tell it is the Gamow lexicographic permutation. Right? A permutation X, we tell it is a Gamow lexicographic permutation when there exists exactly gamma minus 1 permutations which precedes lexicographically your X. Am I right? That X is a permutation, we tell it is a Gamow lexicographic permutation, then there exists exactly gamma minus 1 permutations lexicographically preceding the X. Right? That's why it is ranked as Gamow permutation. So we give one example, say I have n equals to 5 and say r equals to 3. Now if I have to write down all the lexicographic permutations, then I can write it as 1, 2, 3, 1, 2, 4, 1, 2, 5, then 1, 3, 2, 1, 3, 4, 1, 3, 5, then 1, 4, 2, 1, 4, 3, 1, 4, 5, right? Then I can write 1, 5, 3, 1, 5, 4, sorry, 1, 5, 2, 1, 5, 3, 1, 5, 4, and so on. So this is about your definition of permutation, lexicographic permutation. Now what is the problem? The problem is that given n and r, I want to generate all permutations, right? Because this number may be very large, so I need the help of parallel machines. So can we have parallel algorithms to generate all NPR arrangements? So the first algorithms, actually there are two algorithms which came out together, and one of them is OR algorithms. And let us discuss first the other algorithm, then we will come to our algorithm. This is the first algorithm, whatever we will be presenting. This is not based on the lexicographic idea. It will give you all set of permutations, and at each iteration, it will do some manipulation so that after r iterations he will be getting a computation of R elements. What I am telling that it is an R iteration technique. At each iteration, it interchanges one element with another one. So after R iterations, he gets all the populations. Right? That is the idea. Now, one thing you observe that if I have NPR permutations, this permutation makes use of the arrangement of R elements, right? But it is not like combinations. You can think that in this case, it obeys certain distributions. All ones will be there, irrespective of the same occurrence of the elements. Say 1, 2, 3 and 1, 3, 2. The occurrence of elements are same, but only ordering is different. So, if I observe that 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 of them starting with 1s, then you will be getting 12 of them starting with 2s. 12 of them starting with 3s, and so on. Right? So, say for example, this one will be 2, 1, 3, 2, 1, 4, 2, 1, 5, and so on. There are 12 such cases with 2. Right? Basically, that if I have NPR arrangements, then there are these NPR arrangements can be divided into n blocks. Each block is of having size n minus 1 PR minus 1. Okay? Now, what I did, you have NPR. I can divide into that n minus 1 PR minus 1 size blocks. How many such blocks? N blocks. N blocks, each of size n minus 1 PR minus 1. Now the first block contains the elements 1. First element is 1. Now, second block contains the first element 2, and nth block contains the first element n. Is it okay? So, there are n blocks. First block contains 1, second block first element contains 2, and nth block contains first element n. Now, I have to make some arrangement such that this 2 comes first element, n comes as the first element, and so on. Right? Now, if I know that first element is I or 2, now here that what I want, I will be putting all ones here. Just I am interchanging these two elements, I put all ones. Right? And 2 comes the first elements. Is it okay? So, how many elements are having ones? That is n minus 1, PR minus 1. Now, among these n minus 1, PR minus 1, whose first element is 2, second element, all of them will not be 1. Some of them will be 1, some of them will be 3, some of them will be 4, but not 2, because 2 has already occurred. So what I will be doing, I will be dividing again this one into n minus 2 PR minus 2 size groups. That means n minus 1 groups, each of size n minus 2 PR. Right? Now, among these elements will be having 1. These elements will be having 3, these elements will be having 4, and so on. Okay? So that is the idea we want to introduce. So you proceed with R iterations. After R iterations, you will be getting all the desired elements. So let us define first a term IKBK. IKBK is obtained by interchanging the kth element with k plus bk minus 1. At this moment, you assume that bk is one number, one integer. What is bk will come later. So ikbk is obtained by interchanging the kth element with k plus bk minus 1th element. Now, initially I01 means that it is not doing anything because k is 0 and bk is 1. This is also 0. So 0th element is interchanged with 0th element. Nothing is there. That is a standard one. And I also assume x. What it gives you x? X is the whole array of size np r comma n. So it is a two-dimensional array. Two-dimensional array of size np r n. That means you have 1, 2, 3, 4 np r. And here this side you have 1, 2, 3 up to n. So this is a large array matrix, two-dimensional array. That is your x. And initially you assume that each row contains the identity permutations. Each row contains the identity permutations. What it means? That it takes 1, 2, 3 up to n. 1, 2, 3 up to n, 1, 2, 3 up to n. Initially, you assume their identity as. So this is I01. This is I01. This is I01. So what is I01? I01 is the identity permutation. Okay? And what is x? X is a two-dimensional array. Each of size of the array is the npr cross n. Right? So, as I told you that this is an R iteration algorithm. At the first iteration, I divide this npr rows into n groups. This npr rows into n groups. And this division is equally done. So that means there are first group of size n minus 1 pr minus 1. Second group is also of size n minus 1 pr minus 1 and so on. So first group contains the elements 1, 2 up to n minus 1 pr minus 1. Second group contains n minus 1 pr minus 1 plus 1 n minus 1 p r minus 2 plus 2 Similarly, you have the third group, 2n minus 1 p r minus 1 plus 1 3n minus 1 p r minus 1, and you have nth group. Right? So then what I did, I divided this NPR rows into n groups, and the first group contains the rows 1, 2, 3, n minus 1, PR minus 1. So think about the ith row. So ith row, let us assume that is in the B1th group. Ith row is in B1th group. So you can easily find out what is the index of ith row in which group it is. B1th group, so it is a B1 minus 1, n minus 1 PR minus 1 plus 1 to B1 into n minus 1 PR minus 1. That I must be lying between these two numbers. Is it okay? So B, it lies in the Bth group, and you remember the first element, as I discussed, this is first n minus 1 PR minus 1 element, first element will be 1, second one will be 2, and B1th group must have the first element is B1. So what I will be doing, if it lies in the B1th group, then I perform the operations I1 B1. That means the first element is interchanged with B1th element. So B1th group, first element will be B1, 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 and so on. And here all of them are 1. We just have interchange. That is from the definition of this. Agreed? So let these elements or these rows, because I told that what is x? X is the complete set of rows. So you have x, this is your x. Now I got this many elements, they are belonging to your first element is B1. These rows having first element B1. Let us name this as xB1. xB1 is nothing but the set of rows, right, whose first element is B1. And of course, 1 has come here, because I have just interchanged that. How many such rows are there? N minus 1 PR minus 1. Now these n minus 1 PR minus 1 element rows are divided into n minus 1 groups. Each of size n minus 2 PR minus 2. Because this number of elements is n minus 1 PR minus 1. And this I can write n minus 1 factorial n minus r factorial. Is it okay? So I take out n minus 2, I take out n minus 1, n minus 2 factorial by n minus r factorial, which I can write n minus 1, n minus 2, PR minus 2. So what I am dividing? I am dividing this n minus 1 PR minus 1 into n minus 1 groups, each is having n minus 2 PR minus 2 rows. And Remember here, this element is 1. B1th area is 1 and this is B1. I am now thinking about the second element. Now second element, first n minus 2 p r minus 2 element should be 1. So I have to have some procedure to bring interchange these two. Right? Similarly is the case with this and so on. Right? What I will be doing, that I have divided into n minus 1 groups, each is of size n minus 2. So I can get a good number. Let us assume that ith row is belonging to B12 group, B12 group. Let us assume that your ith row now belongs to B12 group. Right? So this B12 group, I will perform the operation I2, B2. That means second element will be interchanged with B2 plus 2 minus 1. B2 plus 2 minus 1. Second element will be interchanged with B2 plus K plus Vk minus 1. Right? Is it okay? So you can find out, similar to this case, the first group contains the row index. Can you tell me what are the row index for first group of XB1? XB1, what is the starting index of this? Starting index, because prior to that there are several such rows. So what is the index of this? Index will be up to this is belonging to other group. So first I need to know the starting index. Starting index is B1 minus 1, right? And n minus 1 PR minus 1 plus 1. Right? That is the starting index of this. What is the end index of this? This one? So it will go up to B1 minus 1, n minus 1 PR minus 1 plus n minus 2 PR minus 2. Right? What is the starting index of this and n index of this? It will be B1 minus 1, n minus 1 PR minus 1 plus n minus 2 PR minus 2 plus 1 to B1 minus 1, n minus 1 PR minus 1 plus 2 times n minus 2 PR minus 2 and so on. So this is the first group of XB1, this is the second group of XB1, third group of XB1 you can define, and there are how many groups? N minus 1 groups. Right? So once you know the group number, let it be B2. So B2 group, what I will be doing the operation that modifies that BI2 B with B2. So that interchange you will be making. Now at the overall, at the kth iteration, let us assume now what happens at the kth iteration. Let us assume that at the kth iteration, right, that I have a subset of, as I define XB1, subset of rows. At the kth iteration, I have a subset of rows x, b1, b2, bk minus 1. Right? And can you tell me what is the number of rows in x, b1, b2, bk minus 1? Can I see when it was B1, only B1, K is 2, when B1, only B1 was there, it was what? N minus 1, PR minus 1. Right? When only B1, it was N minus 1, PR minus 1. When B1, B2, it is N minus 2, PR minus 1. Now, when I have a set of rows where you have performed the operation B1 or B2, B3, that means what? What is the logical indication? Logical meaning of this, that Bk minus 1th group of Bk minus 2th group of of Bkth group, B2th group of B1th group. Right? What it means? That initially I have B1th group, then I got B2th group, and within that I got B3 group. I am talking about Bk minus 1 here, that group. I am talking about this many elements, this many rows, which is of size n minus 1, n minus k plus 1, Pr minus. Now these rows are divided into how many groups? N minus k plus 1 groups, right? So these rows, this size is n minus k plus 1, Pr minus k plus 1. Now these rows are divided into n minus k plus 1 groups, each of size what? N minus k, Pr minus k. So I am dividing these n minus k plus 1, Pr minus k plus 1 rows into n minus k plus 1 groups, each of size n minus k, Pr minus k. Right? Now, can you tell me what is the starting index of the first group? What is the starting index of first group? So, first group starting index B1 minus 1, N minus 1, Pr minus 1 plus 1. Sorry, plus 1 will come later on. So up to this is over. Then B2 minus 1, N minus 2, Pr minus 2 plus B3 minus 1, N minus 3, Pr minus 3, Bk minus 1, N minus k minus 1, Pr minus k plus 1 plus 1. That is the starting index. Right? So this is the B1 minus 1, N minus 1, Pr minus 1 is coming here. Plus, again you have to go down B2 minus 1, N minus 2, R minus 2, and so on. Plus 1 is the starting index. And first group's N index will be whatever it is here. Suppose this is A plus N minus K, Pr minus K. That is the N index. If I assume this part is A. Okay? Now the second group times n minus k pr minus k plus 1 to a plus, why is it 2? No. A plus 2 times n minus k pr minus k. And similarly is the case with the n minus k plus 1 groups. So I know now the starting index and an index. I have divided into n minus k plus 1 groups. So I get the big kth group. I get the big kth group, and for this I perform again ikbk. For the bkth group, I perform this operation. That means the kth element will be interchanged with k plus bk minus 1. Okay? So when k equals to r, you will be getting all the necessary elements and pick up the first r elements. First r elements to get your arrangements. Okay? So let us think little generic way. Suppose you have ith row. I am thinking of the ith row. Now you have to find out what is the value of bk, right, for the ith row. What is the value of, or what is the group number at the kth root iteration of I? What is the group number at the kth iteration of I? So let us assume that J is the serial number of ith row when you have performed B1, B2, Bk minus 1. That means after k minus 1 iterations, then J is the serial number of I. Is it okay? That you have that big 1, 2, 3, this is whole array. Now here you have the ith row. Ith row is this. So J is this one. This index is J. J is the serial number of I within x b1, b2, bk minus 1. Right? Now you have to find out the group number of I. Group number of I is nothing but J divided by n minus k p r minus k. So that if I know I can find out at every iteration what is this serial number or in which group it lies. So once I know this one, rest of the same thing is very simple, just interchange. Now let us write down the algorithm to generate all out of n elements. Initially, let us define an array X where X I j is j for all I. Xij is j for all I. And also we assume that n is equals to n minus 1 NPR minus 1. And also J is equals to, let us assume that J is equals to I. That means I am thinking about the ith row. J is equals to I. So this is your initialization. Now what I have to do? It has to be iterated or iterations. So iterate R times. First, you find out the new J or group number R times, let's say K equals to, not K, R times, okay, K equals to 1 to R. So Bk I have to find out. Bk is nothing but J by N. That will give you the group number. Then you do the interchange K with Bk. Right? Once you have performed this operation, you have to now modify your J and modify your N. What is your J? J is whatever initial J was there minus Bk minus 1 into N. Right? So that will give you now modified J. Initially this, now I have divided into this. So I want to know what is the new J, what is the new position. So that then has to be subtracted. So J is J minus Bk minus 1 into N. And what is your now new N? New N is N by N minus 1. Say, first time it is N minus 1, PR minus 1. Second time it will be N minus 2 and so on. So, can I write it is N minus K plus 1? N minus K. K is 1. K is 1. This K. N minus K. So, N will be reduced by N minus K. So, this is your steps to be iterated. So, to get the one permutations, you need to iterate R times. And you have NPR rows. So, you need basically, if I use a sequential algorithm, you need NPR into R. Right? R iterations, and for each row you will be doing, the complexity comes order NPR into R. Right? Now you observe that if I have to generate the ith permutation, I do not need the help of jth row. Ith independently I can do. Right? While I compute the ith permutation, I can easily independently compute the j, because they are not dependent. So if I have NPR process, then I can generate all NPR permutations after R iterations, because they are independent. So this algorithm can be implemented on any parallel machines, right? And complexity of this algorithm will become order R. So if I have P processors, right, to generate NPR permutations of R, I need NPR divided by P times, and each time you take order R times, right? Because you have the P processors each processor will be generating that many permutations. So what happens that you have the preprocessors and I employ the preprocessor to generate NPR permutations. So each permutation processor will be told to generate NPR divided by P, that many permutations, right? And to generate one permutation you need order of time. So the total complexity of these algorithms using the preprocessor is NPR by P into order R. Now what is the cost of this parallel algorithm? If you remember the definition of the cost of parallel algorithm is nothing but the worst case time complexity multiplied by the number of processors. Cost is worst case time complexity is NPR by P into R plus number of processors. That's the cost, which is order NPR into R. Right? That is the cost. Now let us consider one example to illustrate this one. 5 factorial by 3 factorial is what? 2 factorial? It's a big number. 5 factorial by 2 factorial?
It's like 2 by 3.
5 into 4 into 4 is a big number. 4 factorial by 4 factorial is 24. Let us consider n equals to 4 and r equals to 3. Let us see how it works. I know that there are 24 numbers. Let us assume that we want to do this. Otherwise, you may not feel good, right? So, initially, there are 24 rows. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Initially numbers I told that they are identity. One, two, three, 4. 1, 2, 3, 4. So these are the 24 rows. As I told you that you have NPR rows, which is 24. Now these 24 rows are divided into 4 groups, right? Each group is having size NPR minus 1, which is 6. So this we divided into the 4 groups, each is of size 6 groups. Now this is first group, this is the second group, this is the third group, and this is the fourth group. Now first group, I will be performing the operation B1, this. B1 is 1, 2, 3, 4. So if I have to perform this one, first group B1 is 1, so no interchange, B1 is 1, so 1 plus 1 minus 1 is 1, so no interchange. But here, this will be interchanged, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1. Here, this will be interchanged with this one, right? So it is 3, 3, 3, 3, 3, 3, 1, 1, 1, 1, 1, 1. This will be interchanged with this one. Right? Now I have 4 groups. First element is 1, 2, 3 or 4. Now consider this group. It has a common element, 6 elements. These 6 elements are divided into n minus 1 groups. N minus 1 means basically 3 groups. Each group is what? Of size what? N minus 2 PR minus 2. N minus 2 PR minus 2 is 2. So you have divided into the 3 groups. This is also 3 groups. This is also 3 groups. 3 groups. 3 groups. So first group, I2B1, B2. That first group will be interchanged with the group number plus 2 minus 1. So this one will be interchanged. What is B2? B2 is 1. B2 is 1. 2 plus 1 minus 1. What is 1? 2 plus 1 minus 1 is 2. So for this group, no interchange as it is. For this group, B2 is 2, 2 plus 2 minus 1. So this will be interchanged with this. Three, 2, 3, 2. Right? And for this group, this will be interchanged with this. 4, 4, 2, 2. For this group, there is no interchange. For this group, this will be interchanged with this one. 3, 3, 1, 1. This will be interchanged with this. 4, 4, 1, 1. For this group, no interchange. And here it is 1, 2, 1, 2. 4, 4, 2, 2. Three, 2, 3, 2. 1, 1, 2, 2. Right? Now, this is one group, this is another group, this is another group, one group, each of size 2. Now again you will be dividing into 2 groups and each of size 1 and interchanging that. So what happens in the third group? This will be interchanged. 4, 3. This will be interchanged. 4, 2. This will be interchanged. 2, 3. This will be interchanged. 1, 3. This will be interchanged. 4, 1. This will be interchanged. 4, 3. This will be interchanged 4, 1. This will be interchanged 4, 2. 2, 1. 2, 3. 1, 2. 1, 3. So this is the operations we have done. Now I am telling that first R elements will give you the arrangement. That means what? I am removing this one, I am removing this one, I am removing this one, I am removing this one. Now you check whether you are getting all the cases or not. 1, 2, 3, 1, 2, 4, 1, 3, 4, 1, 3, 1, 3, 2, 1, 3, 4, 1, 4, 3, 1, 4, 2, 2, 1, 3, 2, 1, 4, 2, 3, 1, 2, 3, 4, 2, 4, 3, 2, 4, 1, 3, 1, 2, 3 to 4 and so on. You observe that all of them are distinct and they contain R elements. Total number of elements is n minus npr. So obviously you will be getting npr distinct permutations, right? And you observe also that the ordering is not in lexicographic order, because here 1, 2, 3, 1, 2, 4, 1, 3, 2, 1, 3, 4, 1, 4, 3, then 1, 4, 2. This is not lexicographic precedence, right? Similarly is the case 2, 1, 3, 2, 1, 4, 2, 3, 1, 2, 3, 4, 2, 4, 3, 2, 4, 1, and so on. So it is not lexicographic permutation, but it generates all the distinct permutation of npr size of R elements out of n, right? The disadvantage with this technique is that it needs a huge array, npr rows and n columns, right? And if I use P-processors, the algorithm can be made is adaptive, since the generation of permutation of one permutation does not depend on another one. So adaptiveness holds good. So it can be implemented on any parallel machines using pre-processors. The complexity will become order npr by p into order. So this is one algorithm. Next algorithm we will be discussing on different data structure. So I think I will not be covering today that one. We will be discussing this one in the next class. But before that, I assume that you have knowledge on balance binary. See, we designed a new data structure based on the height balance binary tree, right, which has helped us to generate the permutations, and which is also adaptive and can be implemented on any machines, right? Now, if you remember that height balance binary tree is a binary tree where the height is of order log n and the height of the left subtree minus height of the right subtree is plus minus 1, lying between plus minus 1. That is, height will be left side height may be minus 1 more than the right subtree height, or plus 1 of the, or maybe of the same height. Right? And insertion of any no elements in the balanced binary tree is also order log n. Deletion also takes order log n. And we wanted to make use of this data structure. We want to modify these data structures so that this can be used for our permutation and elements generations. See, we define a problem is of that structure that given m records which form a balanced binary tree and an argument k, your aim is to find a non-negative integer u such that if I insert k plus u, or the rank of k plus u in that m record is u plus 1. And if you get that u plus 1, you insert that node at the u plus 1th area and then rebalance the tree for future generation. So that is the problem. So first we will be discussing about this problem and we will discuss how you can solve it. Then we will see how we can make use of it to generate the lexicographic permutations. Because our algorithm is to generate the lexicographic permutations. We will be also discussing another permutation algorithm, which is that generally we have n elements and r distinct objects you want to select. But suppose what happens that n elements which are not distinct. The problem is a little different, that if the elements are not distinct and you want to generate R out of A, then some of them will be repeating again. So how to generate that computation also we'll be discussing as a third algorithm. So let us stop here and discuss in the next class.